All right, everyone. I'm recording this on my front porch, so if you hear any dogs barking or cars driving by, I apologize. But I wanted to kind of get with you guys about the next concept that we have in our textbooks. Um, this particular, chapter is all about chi-squared testing. I know it's CHI, but it's chi-squared. Here is an example straight from the textbook, so you can follow along in the textbook if you want, but I have everything here if you don't. It says, does your zodiac sign predict how successful you will be later in life? Magazine collected the zodiac signs of 256 heads of the largest 400 companies. And the table shows how many, what the signs were for each of those CEOs. All right. It says we can see some variation in the numbers of births per sign. There are more Pisces, right? 29 Pisces. But is that enough to claim that successful people are more likely to be born under some signs than others? All right. So, um, the first type of chi-squared testing that we're going to be talking about is goodness of fit. That's the only one that's going to be addressed in this video. There's also one for homogeneity and one for independence. Those videos will follow soon. All right. Um, if these 256 births were distributed uniformly across the year, we would expect about 1/12 of them to occur under each sign of the zodiac, since there's 12 months in a year. That suggests that 256 divided by 12 are about 21.3 births per sign. So we want to figure how closely these observed numbers, that's the numbers that are in these, in here, how closely are these numbers here to 21.3, basically. Um, and again, that's going to be our null hypothesis, the 21.3. So it says a hypothesis test to address this question is called a goodness of fit test. All right. So goodness of fit involves testing a hypothesis. We have specified a model for the distribution that we want to know whether it fits. There is no single parameter to estimate, so a confidence interval wouldn't make sense, guys. Um, you know, the tests that we've learned to this point just don't work, all right? Because we have 12 different, proportions to worry about, not just one. So this one is a whole lot different than what we've seen in the past. It says we need a test that considers all of them together and gives an overall idea of whether the observed distribution differs from the hypothesis one. All right, so there are assumptions that we have to have for this particular thing. Luckily, um, there's not that many assumptions for this particular, concept. First, we have to have the counted data. It says that the values in each cell must be counts for categories. So we have to have categorical data. We can't talk about how many, we can't use means and averages and stuff like that. We have to, in proportions, we have to have counts. All right. So, we can't apply this to proportions, percentages, measurements, that type of thing, because it has to be counts. This data must be independent. It says the responses counted in the cells should be independent. Um, so these Fortune 500 executives are not necessarily a random sample, but it's reasonable to think that their birth dates could be randomly distributed throughout the year. So we have to, it says the individuals who have been counted should be a random sample from the population of interest, and our sample is less than 10% of the population. And then here it says we have to have enough data for the methods to work, so we usually check the expected cell frequency condition. We need to see at least 5 counts in each cell. All right. So before we were using 10, this time we are using 5, because we have so many different, categories. It might not be, might not be able to get 10 all the time. So it needs to be at least 5 for this. So here is how the calculation goes, this chi-square testing. And this formula is for all 3 types, both um, goodness of fit, homogeneity, and independence. So it's the same formula each time. So what we're going to do is we are going to take the sum of all cells. So each one we're going to take our observed number minus what we expect, We are then going to square that, and the job of the squaring here, what that does is it makes this number definitely positive, because we don't do negative values here, because the negative values would be canceling out some of the positive values when we do the summing. So that's why we do the squaring here. And then you are going to divide by the expected value. This is if you were going to do this manually without a calculator. All right, and the symbol for this is x squared, but the x is kind of like a fancy x, and that is the Greek letter chi. That's why they call this chi-squared testing. All right, it looks like this when it's spelled out. Right now, one big thing here is our degrees of freedom. Normally, our degrees of freedom, that's our sample size minus one oftentimes, but this time it's not that. Because we have 12 different zodiac signs, our degrees of freedom is going to be 11. So it is, whatever categories you have, however many categories you have, minus one, that is going to be your degrees of freedom. All right, now it says if the observed counts perfectly match with the expected value, chi-square would be 0. So for instance, if we're up here and it was 21.3 and 21.3 and 21.3, that would give us 0 when we summed all this up, if the data matched perfectly. So it says the greater the difference is positive or negative, the larger x squared becomes. If the calculated value is large enough, we'll reject the null hypothesis. And the question is, what is large enough? It depends on how many degrees of freedom you have. I mean, if you've got 50 different degrees of freedom, those small numbers squared and summed up is going to add up to a larger number. Where if you've only got 5 or 6 degrees of freedom, you're not going to get a very big sum when you add them up. So we use our technology to find a p-value, and that way a p-value is going to help us determine a lot better compared to our x squared or our chi-squared value. All right. So rejecting the null, what does it mean? When our p-value is small enough and we reject our null, that's going to mean that we have something definitely going on, right? So if we have a larger p-value, that means that we are going to fail to reject, and it doesn't appear that really anything other than, you know, uh, so in our example here with the CEOs, if we fail to reject the null hypothesis, it appears that um, zodiac sign doesn't have any bearing on how successful you're going to be, right? All right, so let's take a look here. So here we have the problem. We have counts of 256 executives in 12 zodiac signs. The natural null hypothesis is that birth dates of executives are divided equally among the zodiac signs. So our question is, are CEOs more likely to be born under some zodiac signs than others? So first, we're going to lay out the data. We have our null hypothesis: births are uniformly distributed over zodiac signs. Our alternative hypothesis is that these births here are not uniformly distributed over zodiac signs. And I know they're not all the same. This 21.3 line right here is where it should be. But notice we've got some over, we've got some under. So just on initial inspection, it appears that there's not really that much of a difference between what we see here and what we should normally see. All right. We're going to go down here. We're going to check our assumptions. All right. So our counted data condition, we have at least 5 counts. So that's good. We've got, our, these are all counts. We've got our independence. The birth dates of the executives should be independent of each other. This is not, random executives, but we can expect their birth dates to be random. So that's okay. The expected cell frequency, we have at least 5. So that condition is satisfied. So we're going to go ahead and do a chi-squared goodness of fit test. All right. So what they do here is they go ahead and I'll show you in a second how they get all these numbers right here. But it said the expected value is 21.3. So for each one, we take the value that we observed and subtract from it the 21.3. We square that value and then we divide it by the 21.3, and then we do that for each one and add them up. So if you take a look up here, the first data value here is 23. That's this test here. The second data value was 20, which is right here. And then they continue to do that for all of the data values, I believe, if I'm not mistaken. I have the chart over here. Yeah, so here's the first value, 23 minus the expected. We get this value, we square that value, and then we just continue and we divide that by the expected value, and then we just add all these up, and that's how we get our sum. Remember, this sign sigma here means sum. All right, let's go back to where we were. So the p-value that we get is 0.926. That p-value is actually pretty large. All right, so it says the p-value of 0.926 says that if the zodiac signs of executives were in fact distributed uniformly, an observed chi-square value of 5.09 or higher would occur about 93% of the time. All right, move this decimal 2 places. So this is absolutely not unusual. So we fail to reject the null hypothesis, and we conclude that these data show that virtually no evidence that executives are more likely to have certain zodiac signs. All right. So here's the procedure overall. All right. First, we have to find the expected values. So, we have to find out what we should expect to see on this last one. It was, 1 divided by 12. So that, and then there was 256. So 1/12 of 256 is 21.3. We have to, find all of our, they call them residuals. So we've got observed minus expected. We square that value. Again, that makes those positive. We divide by the expected. We find the sum of all of those. We find our degrees of freedom, and then we go ahead and test our hypothesis. All right, so that's how it's laid out. Alrighty, so now here is a question about how big is big. For instance, this 5.094, if we have gotten that for a z value or a t value, or a z-score or t-score, that would have been far outside from the center. So why is that not a big number for, why is that not a remarkable number for chi-squared? Well, the problem is the degrees of freedom. Okay, this is a curve for a 5 degrees of freedom curve, and this is a curve for a 9 degrees of freedom curve. They're using the example of 10 right here. A 10 for 5 degrees of freedom, that sum is big because you've only got, five or six different things that you're adding up. And adding up to a 10 would be kind of far out there. With the 9 degrees of freedom, it's not as far out on that curve because you've got 9 or 10 things that you're adding up. Values that you're adding up that's going to account for that number, so it doesn't count as much. So whenever you've got, basically it says right down here, it says whenever you got larger numbers of degrees of freedom, those larger numbers are going to mean a little bit less. All right, so it says our test for zodiac birthdays had 11 degrees of freedom. So the relevant chi-squared curve peaks at 9 and has a mean of 11. Knowing that, we might have easily guessed the calculated chi-squared value of 5.094. That really wasn't going to be that significant. Okay, here you see a TI emulator. It's called TI Smart View for the TI 84 Plus. This is a trial version I downloaded for 90 days. So if you don't have your calculator at home or you want to do this on your screen instead, you can just search for TI 84 emulator, and you can download this and for free and use it for 90 days, which is, hey, great for us through the end of the year. So the first thing you want to do this chi-square testing is you need to be able to put in your data into your lists. So here's our lists. Actually, I think we just hit the stat key. All right, so we got stat, and we're going to hit edit. So we're going to go into edit. And in list 1, we want to drop in those counts. All right, so we got 23, enter, 20, oops, back that up, 20, enter. And I'll probably cut some of this out. All right, so it doesn't take too long. 29. All right. So now in list 2, we want to put in the expected values. And we know the expected values was going to be 1/12. So we're going to divide by 1 divided by 12. All right. So 1/12, basically 1/12 of the total should have been here. So we're going to do 1 divided by 12 for each one of these. Yes, you do have to do it for each one of these. I'm sorry, but hey, that's the way it works. Okay, so now we've got matching data for all of our second column. Now in the third column, this is where we're going to go ahead and do our, we're going to figure out, we're going to actually turn these into the expected values. So what we're going to do is we're going to quit out of this part, second quit, and then we're going to do the sum function, right? So we're going to go to list, and we go over to math, right? We have a sum function, number 5. And what are we going to sum? We are going to sum list 1. So second, list 1 is right here. All right, close the parentheses. We're going to take and sum that with list 2, second L2. And then we're going to store those values. And in the textbook, it shows them, and in this presentation I showed you, it shows them storing them right back into list 2. You can do that if you want to, or you could do it in list 3. I'm going to go ahead and store it in list 2 because really we don't need those values that are there. So it's going to go ahead and replace those values. So when we do that, it says, hey, these are the values that we're storing. Now, if you don't get this number, and the first couple times that I did this yesterday, I did not get this number. And the reason is that I had not put my data in correctly into the calculator. So when I was initially putting in those counts that we had for those numbers of CEOs, my data was not right. Okay, so if you don't get these values, go ahead and try to fix anything that might be wrong. Now let's go ahead and look back at those lists. So I'm going to hit second list. Oops, sorry. I don't have to hit second. So let's hit edit, and you guys can now see that those 1 divided by 12s, those 0.833s have been replaced, right? We have all of the data in there that we need because all we need is observed and expected. That's all we need, right? Those are the only things we need for this particular test. So we're going to quit out of this part. And the way that we get to our goodness of fit test, we do stat tests, and we just go down our list. You see all these tests that we've been running for a very long time. We're going to go down here to our chi-squared goodness of fit test. And there it is, chi-squared goodness of fit test. All right, we're going to go ahead and hit enter. All right, and it asks us for a few things. Where is our observed values? Well, our observed values, we did put them in list 1. Where is our expected values? We put them in list 2. It also asks for our degrees of freedom. Now, our degrees of freedom for this particular problem was 11 because we had 12 different cell values because of the 12 different zodiac signs. So 12 minus 11 or minus 1 is 11. So we're going to have 11 degrees of freedom. We're going to go down here and tell it to calculate this. And once it calculates it, we get our chi-squared value. We get our p-value. It shows our degrees of freedom. And then it does also show us some component stuff that is not very important right now. We'll talk about this stuff later on. These are the individual values that you get. If you look back at that table that I had in the presentation where it showed all the values, these are the values that pop up when you actually work out the problems. But again, with this type of a p-value, if we take this decimal and move it over here, it says that 92.6 or 92.7% of the time, about 93% of the time, we would get a value, you know, that far out. So again, that's, not very exciting, no real insight there. So we fail to reject the null hypothesis, and it appears that your zodiac sign doesn't have anything to do with your level of success, at least in this particular set of data. All right, guys, good luck on those problems. All right, and this is the problems that you guys are going to do. Page 694, numbers 13, 18, and 21. I am severely reducing the number of problems that we're doing, guys. It is important that you get this stuff done, and I don't want to take up a ton of your time. But when I do give you the problems, guys, you really, really, really need to do these. I'm going to go ahead and show you the problems on here so you don't actually have to get on the website to look at the e-textbook. If you don't have your textbook at home. So I'm going to go ahead and put them up here. So the first one here is about dice. So if you're having a problem reading it, it says, after getting trounced by your little brother in a children's game, you suspect the die he gave you to roll may be unfair. To check, you roll it 60 times, recording the number of times each face appears. Do these results cast doubt on the die's fairness? So again, these would be the values that you would end up putting into your TI calculator, and think about what you should get. All right. Number 18, a salesman who is on the road visiting clients thinks that on average he drives the same distance each day of the week. He keeps track of his mileage for several weeks and discovers that he averages 122 miles on Mondays, 203 miles on Tuesdays, 176 miles on Wednesdays, 181 miles on Thursdays, and 108 miles on Fridays. He wonders if this evidence contradicts his belief in a uniform distribution of miles across days of the week. Explain why it is not appropriate to test his hypothesis using the chi-squared goodness of fit test. Offspring of certain fruit flies may have yellow or ebony bodies. Ebony is black, for those you guys that don't know that. And normal wings or short wings. Genetic theory predicts that these traits will appear in the ratio of 9 to 3 to 3 to 1. In other words, 9 yellow, 3 normal, 9 yellow normal, 3 yellow short, 3 ebony normal, and 1 ebony short. A researcher checks 100 such flies and finds the distribution of the traits to be 59, 20, 11, and 10, respectively. Are the results this researcher observed consistent with the theoretical distribution predicted by the genetic model? If the researcher had examined 200 flies and counted exactly twice as many in each category, what conclusion would he have reached? And why is there a discrepancy between the two conclusions? So, run these two, all right, one with 100 flies and one with 200, and see why is there a difference between the two? Why is that different?